Alright, hello everyone. So let's look at calculating some equilibrium constants for a specific equilibrium reaction. So for this case, we're given at 700 degrees Celsius in a 200 liter tank. This contains 1 mole of carbon monoxide, 0.2 mole of carbon dioxide, and 0.4 mole of carbon at equilibrium. Important word, so this reaction is already at equilibrium. And then the following reaction or equilibrium is the one that we are considering. We're then asked to calculate Kc for the reaction at 700 degrees Celsius. And then some subsequent questions. So, right, let's go ahead to calculate Kc, so in other words, the equilibrium constant for this reaction at 700 degrees Celsius. So our first step, of course, let's write down the equilibrium constant expression. So our products in this case are carbon monoxide. So that means we have CO, and it's an equilibrium constant expression. So we're interested in equilibrium concentrations, and it has a stoichiometric coefficient. So we square that. Of course, you can leave out the equilibrium, so meaning COEQ. But I like to be explicit, so we remind ourselves we must use equilibrium concentrations, right? On the reactant side, we see we have CO2, right? So CO2, equilibrium. And then we see we have carbon solid. And as we know, the carb solids don't have concentrations. So in other words, we leave them out of equilibrium expressions, or they have, in other words, they have the concentration of unity, so meaning they have a value of 1. So we're not going to include that in our equilibrium constant expression. So now we have to calculate that, and hopefully you realize, well, we're given number of mole, we're not given concentration, so we must also just, perhaps here as an aside, we must calculate each of these values. So let's go ahead and do that. So the equilibrium concentration for carbon monoxide is, we're given that it is what again? It's 1 mole, so that's 1.0 mole in 200 liter tank, and CO2 equilibrium is 0.20 mole, also in a 200 liter tank. Alright, you can calculate that separately, or you can immediately plug it into the equation there at the top. So CO, that's 5.0 times 10 to the negative 3 molar, which is 1.0 times 10 to the negative 3 molar. Of course, technically you keep all your decimal places in these calculations here. Now plug it in here, so that means we take 5 times 0 times 10 to the negative 3. Remember to square it. And you take 1.0, take all the decimal places, times 10 to the negative 3. There. Right, so these technically don't have decimal places, but just if you're calculating something, remember to carry all your decimal places, and you should get a value of 0.025. Okay. Now you might say, okay, this is very easy. What's the point of this example? The point actually comes in the B question. It says, now calculate Kc for the reaction, also still at 700 degrees Celsius, if the amounts at equilibrium in the 200 liter tank are 1 mole of CO, 0.2 mole of CO2, and now 0.8 mole of C. So what's changed? Well, the number of mole of CO hasn't changed, the number of mole of CO2 hasn't changed, and the number of mole of carbon has changed. So we haven't changed anything in terms of our concentrations. The amount of mole of carbon has changed, but carbon doesn't appear in the Kc expression. The temperature hasn't changed, the volume of the tank hasn't changed. So we haven't disturbed the equilibrium because we haven't changed the temperature, we didn't change the volume, we didn't change the concentration of any of the reactants. The only thing we changed is the amount of the solid. And the solid, granted, the solid might take up a bit more volume, but I mean, that's negligible. The solid does not influence the equilibrium directly in this case. And hence, nothing happens to the equilibrium constant. So, I mean, you can go ahead and you can calculate Kc again directly, but Kc should have exactly the same value as it had in A. And this just shows you that the solid does not have an effect on the Kc expression, right? So, and that's because it's not included in the Kc expression, all right? And also, Kc is dependent on the temperature, and it's the only time when Kc changes is if we were to change the temperature, all right? All the other times, the concentration values would proportionally shift to keep Kc constant, all right? So your Kc value will always remain constant, and all the other values will vary according to that. All right, so nothing changed here. So your Kc value is the same, and in fact, your concentration values remain the same because you didn't really do anything here to do anything. Okay, and that concludes then actually what C also wanted us to do, is to say, well, compare your results of A and B. Does the quantity of carbon affect the value of Kc? No. The only thing that will affect the value of Kc, like I said, is the temperature, because K, the equilibrium constant, is a function, K is a function of temperature. So the only thing that can make your K value change is temperature, and not the concentrations, because your concentrations will shift in their different amounts, but their ratio will remain the same, right? So in other words, even if you disturb the equilibrium, then the equilibrium ratio, so then in other words, both concentrations will change again to give you the same Kc, granted that you keep the equilibrium at the same temperature. If you change the temperature, then that's going to change the equilibrium constant value. Okay, so the only thing that can change Kc is the temperature. Changing any concentration value will then just affect the other concentration values. Changing the amount of carbon in this case doesn't affect anything, because carbon doesn't even appear in the Kc expression, and hence, because it's a solid, and hence it did not even affect the concentration values, because it does not disturb the equilibrium in any manner. It also does not disturb the equilibrium in any manner, like for example the volume. So in other words, it did not have an effect on the concentrations in that way as well. Okay, so this example was to show that if something doesn't appear in the Kc expression, it will not be able to disturb an equilibrium in any way, and it will not have, definitely will not have an effect on the Kc value, because K is only a function of temperature. And if we do not change the temperature, then we will not change K. All right. Thank you for watching, and I'll see you in the next video.